Hey, what's up everybody? Welcome back to the channel. Today I'm back out here at the Lake Wilson Reservoir in Oahu. In this video I'm just doing a follow-up to a test that I did a couple videos ago where I hooked up an 18-volt Ryobi battery to a Water Snake T24 trolling motor to see if I could get more speed out of it. And while that test did have some interesting results and information that I was able to pull from it, I don't think the test was done as well as I could have done it. This time I'm on my Pelican 110 HD. I'm using my DIY through-hole motor mount. This is the new one that I made. In my last video where I did the DIY versus Bixby test, I had a different motor insert. So I went back and redesigned this one to where it sits flush with the base of the kayak. It does have a locking dowel, so it locks into place. I added a slot here so you can use just the ruler to straighten out the prop to get it to pull out or back out through the hole. This one uses a lot less plastic than the last one I printed. If anyone is interested in printing one of these adapters for yourself, I'll put a link in the description so you could pull the file off of Thingiverse, and it's just up there for free for anyone who wants to print one. Anyways, so other than the new motor mount that I printed, I also got the watt meter. It tracks voltage, amperage, watts, and you could set it to where it tracks, or this one tracks the total power consumed. I have it set to watt hours. Since starting this intro, I've used 2.9 watt hours of power. With the power meter that I'm using, I also have the same PWM motor controller, and I have updated the 18-volt battery pack that I was using. When I switch over to the other battery, I'll open it up and show you how I have that set up. And I've got my Garmin Striker 4 just so I could track the speed. In this video, I'm going to show you the actual current being pulled for each battery pack at different speeds that I'm going. I'm going to show you how much more power is actually being pulled versus the speed that I'm going. So then after I'm done doing the test at different speeds, I'm going to go back over everything, talk about the numbers that I saw, and talk about why you would or wouldn't want to use an 18-volt battery with a 12-volt trolling motor. Okay, so to get this started, I do have the motor connected to the AmperTime lithium iron phosphate 12-volt 50 amp hour battery. It's the same battery that I've been using for all the tests I've done out here. So I have the PWM set to 40% right now. As you can see on here, I'm pulling 22 watts, and that's getting me pretty consistently about 1.2 miles per hour. If we're pulling 22 watts to go 1.2 miles an hour at 40%, if this was a linear power change, when we're pulling 40 watts, we should be going almost 2.5 miles an hour. So let's turn the speed up until we get to 2.5 miles an hour and see what actually happens. Okay, so we're hitting 2.4 when the wind isn't blowing in our face. If the power increase was a 1-to-1 linear change with speed increase, then we should be at 80% on the PWM and 40 watts of current being drawn. However, while we are at 82% on the motor controller, we are actually pulling 100 or almost 120 watt in order to get that speed increase. So as you can see, it's not a 1-to-1 change between power and speed. Since we've seen what it looks like at 80%, let's go ahead and kick it up to 100% and see how much more speed we actually get from this. At 100%, we're up to 200 watts. That gets us 3 miles an hour. So in order to increase our speed by half of a mile an hour, it required nearly 100 extra watts. So now as you can see, we have it plugged into the 18-volt battery, and we are pulling 20 watts at 27%. And that same 20 watts has us moving at 1.3 miles an hour. The slight speed discrepancy between the 1.2 we were getting on the 12-volt battery and the 1.3 we're getting now is that the wind is slightly at my back. The battery's putting out 20 volts right now, but we're still going the same speed, and that's because the motor speed on a DC motor is dictated by the amount of actual power flowing through it. So that's not to say the amount of amps or the amount of volt, but a combination of the two to give you watts, which is the actual DC power flow. So even though we're showing 20 volts, we're only pushing 1 amp right now to give us the 20 watts that we need to maintain the speed. So if we increase to the same 120 watts that we were at on the 12-volt motor, we should be able to see our speed climb to the same 2.5 miles an hour we were getting before. So you can see that at the same 120 watts that I was pushing with the 12-volt battery, I'm getting the same speed with 120 watts out of the 18-volt battery. Because it doesn't matter what the voltage of the motor is, it matters about the amount of actual power that you're pushing into the motor. So that being said, how much actual power will the 18-volt battery push? And I'm only going to run this for a very short time because, as you can see on the power meter in a second, it pulls considerably more power than the 12-volt does. Even though the 12-volt battery will only pull 20 amps, the 18-volt battery will pull 30 amps and push over 500 watts. And that didn't even get us up to 4 miles an hour. If we're getting 3 miles an hour at 200 watts, and we're barely able to almost hit 4 miles an hour with a little over 500 watts, which is more than twice the power for almost no gain in speed, what could be the benefit of running an 18-volt battery instead of just a 12-volt battery? And mostly, that comes down to the current that's flowing through the wires. You're able to get the same 200 watts that you would out of the 12-volt battery, but it requires less amps. Pushing 200 watts, we're still getting about 3 miles an hour, but as you can see, the amount of amps is a lot lower. The amount of amps flowing through the wiring in your system has a big part in how much heat actually builds up in the wires. So the coils on the motor, all the wires running from the battery to the controller to the motor itself, all those wires will last a lot longer if they have less heat buildup in them as you're running it. And it's easier on the batteries if you have a lower discharge rate. So your 18-volt battery, if you maintain the same wattage output, should survive longer than a 12-volt battery will. Now that difference isn't going to be immediately noticeable running lithium batteries, because lithium batteries do typically last a long time anyways, but battery longevity is an added benefit to running an 18-volt battery at a lower output. Most trolling motors use a brushed DC motor, and a brushed DC motor has a watt limit caused mostly by the sparks that generate as you push more watts through it, which builds up more heat and destroys the motor. You can run a brushless DC motor with a propeller, much like they do with the e-foils. The brushless DC motor doesn't have the same issues with the sparks, and it doesn't produce nearly as much heat, so you could run those at a much higher rate and make it go a lot faster. Granted, those motors are typically more expensive, but it is something that you can do. So if you want to go faster on your kayak, you're going to have to apply more power, but you're going to have a motor that can handle that. Simply running an 18-volt battery with a 12-volt motor is not necessarily the way to go. And if it's a brushed DC motor, most likely all you'll do is destroy your trolling motor and have to get a new one. So I hope you guys found this video useful. If you did, maybe share it with your friends. Or if you have any experience with overvolting your trolling motor, maybe leave a comment down below and let us know how it went for you. Anyways, I will catch you guys on the next one.